Hello, everyone. Welcome, everyone, to today's webinar. My name is Dr. Mary Lesser. I'm a faculty member and clinician at UC Berkeley and UCSF Benioff Children's Hospital, Oakland. I am also here today representing the Research Dietetic Practice Group of the Academy of Nutrition and Dietetics as the chair for our group. I will also be serving as moderator for today's program. Today, we aim to take a step back and provide some foundational information to support the audience's interaction with and understanding and application of gut microbiome research. So we're very pleased to offer this webinar to you as a collaboration between three groups as shown here. IFANS, or the Institute for the Advancement of Food and Nutrition Sciences, is a nonprofit scientific organization that advances food safety and nutrition science for the benefit of public health by bringing together scientists from industry, government, and academia. The Academy of Nutrition and Dietetics Research Practice Group brings together registered dietitian nutritionists with a particular interest in nutrition-related research. And any audience in the audience with this interest are encouraged to join for additional value and benefits of this membership. I'm honored to be a member of this practice group and the current chair for this year, and to serve as your moderator for this event and our program today. Finally, the American Society for Nutrition's Nutritional Microbiology Research Interest Section, or RIS, brings together investigators who explore interactions between dietary compounds and the microbiome. ASN is also an excellent organization. I encourage anybody who is interested to join to and experience the member benefits there as well. This webinar is approved for one continuing professional education credit by the Commission on Dietetic Registration. Access to the certificate of participation will be provided to participants shortly after the webinar. So before we jump in, let's quickly touch on some logistics. On this slide, you see the control panel, which should be visible on your desktop. We encourage you to submit questions through the program by typing them into the questions box. Only the organizers will be able to see these questions. Also, before we begin, we wanted to get a sense of our audience and who is here today by trying out one of our live polls. So before we show you the poll question, the instructions for how to complete the poll are on this slide. You can find the poll by either going to the web address shown or by using your phone, first texting IFANS or IAFNS Connect 300 to the number shown. We're going to give everybody a couple of seconds here to choose one of these options to participate in today's poll. All right, so for today's poll, our question is, which statement best describes how you currently interact with the gut microbiome science or research? So we're going to give everybody a few seconds to respond, so we can see what who is here and what we have in terms of our audience.
And Mary, I think I'm going to just refresh this because it might be, the app is a little bit stuck. So just 1 second.
No problem.
All right, looks like we have some responses here.
Yeah, excellent. So let's take a look. See, we have some more responses coming in. Looks like we have just around 175 participants today, and of those who have been able to participate in our poll, looks like the majority, although pretty close, is that we have those in the audience who are required to read and understand gut microbiome science at a high level, or those that are actively engaged in gut microbiome science and research. We do have also those in the audience a little bit less so, that they're aware of gut microbiome science but only follow it peripherally. And then those that this is a completely new field to me. So looks like we have a pretty nice spread of participants. So hopefully with our speakers today, we can all engage in one of those levels. Thanks for participating in the poll today. All right, so let's get right into today's program. The learning objectives are shown here on the slide, and to include supporting participants' abilities to apply fundamental elements of study design in the field of gut microbiome and nutrition research, and also to describe important elements to consider when reviewing, interpreting, and applying findings from gut microbiome research studies. All right, so with those objectives in mind, I am pleased to introduce our very first speaker today, Dr. Sarah Comstock. Dr. Comstock is an assistant professor in the Department of Food, Science, and Nutrition at Michigan State. Her research interests include a focus on early nutrition. Excuse me, I just lost my place on your bio. So sorry about that, Dr. Comstock. Her research interests again include a focus on early nutrition, including neonatal and maternal influences. The objective of her work is to identify immune or microbial targets which can inform the basis for nutrition interventions. Dr. Comstock will be focusing today on design of gut microbiome studies. We will turn it over to you, Dr. Comstock. Thank you again.
All right, thanks so much for that introduction, Dr. Lesser. Let me just get my screen organized here. All right, so today I'm going to be discussing study designs for considerations for diet and microbiome research. These are my disclosures and conflicts of interest. So I'm first going to start off with why we want to address this topic, which I'm sure many of you have come with your own reasons why you're interested in the topic. I'll hone in on our specific research focus for today. I'll talk a little bit about what I've learned by doing. I'll give some examples from other people's work. Then we'll dive into important intervention design and recruitment considerations, sampling methods, as well as the important metadata to collect. So why? An ounce of prevention is worth a pound of cure. So it's much better to determine some intervention details pre-trial to make sure that your results are generalizable, that your results make sense, that your data is interpretable. And some of these important details include any dose of the nutrition intervention, the timing of your nutrition intervention, formulation or food matrix considerations, as well as thinking about whether or not the food or food component that you are studying can actually reach the microbes of interest. And finally, considerations about the study population. Who are you studying? And are those people representative of the people that you expect to be able to apply your results to? All of these design decisions impact the use and generalizability of the study results. So I have here a picture of a cute little mouse in his laboratory cage, a picture of the diet that your typical mouse consumes, very purified, pretty standard. And when we compare that to what humans eat, you can see that humans have a lot more choices, a lot more variety. They eat in different ways. They're out in the real world. And all of this is just to say that mice are not humans. And this is also true when we look at the gut microbiomes. So what you see presented here on the left is just comparing the microbiome compositions of non-human primates, rats, mice, and humans. And you can see that the composition based on this plot is very different between humans and mouse and rats and even non-human primates. And on the right-hand side, it's also comparing the microbiomes, but now it's not just considering the composition of those microbiomes, but it's also taking into account the abundance of those different microbes. And so now there's more overlap between the human, rat, and non-human primate microbiomes. However, the mice are still off on their own. And there is a lot of research in microbiomes using murine models. And all this is to say that today we're going to be focused on human studies because we want to focus on what's most generalizable. And in the end, we'd like to apply our results to humans. And so today's talk is going to focus on human studies. We can learn a lot about mechanisms from mice, but what we really want to do is understand what's happening in humans. And so I've been doing this a little bit in my career so far. I have here the motto for a club I belonged to as a child. It's sort of the unofficial motto, learn by doing. And what this means is sometimes you just got to dive in, try something out, and realize what works and what doesn't work, in order to make progress. And that's really what we all do as scientists, right? We're diving in, we're trying things, we're seeing what's working and what's not working. So today I'll bring my lens from having conducted a few diet microbiome studies, as well as the literature's view and information from the literature. So I want to start with this example from the literature, and it's certainly not the first example of a diet microbiome research study, intervention study, but it's one that's commonly cited and is well done and is interesting. And that is this paper by Lawrence David from 2014, where diet rapidly and reproducibly was shown to alter the human gut microbiome. And I'm just going to show you some data. What you can see on this plot on the x-axis is the day. So from -4 days to the day the intervention was started to 10 days post the start of the intervention. And what you'll see on the y-axis are different variables. And on the left-hand side, you'll see people taking in a plant-based diet. And on the right-hand side, you'll see people taking in an animal-based diet. And so these are just the nutritional constituents of those diets. We have fiber on top, fat in the middle, and protein in the bottom. And you can see that the intervention worked, right? So these people were consuming a lot more fiber on the plant-based diet, less fiber on the animal-based diet. So the diet intervention worked. So next, I wanted to show you the microbiome data. So in the top two panels, we have the alpha diversity of the microbiome. And this is just a measure of within an individual, how diverse is that person's microbiome? How many different microbes are there? And are they there in sort of even percentages, or are they there in uneven percentages? And what we can see is even though the diet very much changed, the alpha diversity of these individuals' microbiomes did not really change very strongly. In the bottom two plots, we see the beta diversity. And in the shading is when the intervention occurred. And on the plant-based diet, we see that this beta diversity, which is a comparison across different individuals' microbiomes participating in this research study. We see in the plant-based diet, this doesn't really change. And in the animal-based diet, each person's microbiome at the end of the intervention was less similar to itself at the beginning of the intervention. So this was comparing the own person's microbiome at the end of the intervention to their own microbiome at the beginning of the intervention. And so they were less similar to themselves after this intervention. And one nice thing about this study design, which you might want to make note of, is they included a colorful dye when they started the intervention. And the arrows indicate when they saw that dye come out in the individual stool samples. So that's a nice touch that they did in this study. And all of this is to say that it's complicated and difficult to observe strong changes in the microbiome when you're doing a dietary intervention. And even if the diet is not varied, even if the diet is a monotonous diet of just a food supplement, so this I think they said was an Ensure supplement, I'm not sure, but it's just a drink that contains defined nutrition. And two of these individuals, subjects 11 and subjects 12, consumed that meal replacement and didn't consume anything else. And so this is the food intake on the bottom. And you can see this other individual just was eating whatever they wanted to eat, okay? What you notice is even though they had a very monotonous diet, subjects 11 and 12, their microbiomes shifted a lot, even with these dietary monotony. And this is just to remind everyone here that diet is not the only thing that determines microbiome composition. And that's why we need to collect some important metadata, which we will talk about a little later. And this was a nice paper published back in 2019 by Dr. Abigail Johnson and Dr. Knights at the University of Minnesota. Another important feature I want to point out from the David et al. Example is that measuring microbial function can sometimes be a much stronger way to detect an impact of your intervention. So although they saw only mild changes in alpha and beta diversity with the two interventions, when they looked at measures of microbial function, such as concentrations of short-chain fatty acids, or the activity of glutamine aminotransferase or methyltransferases, you can see much stronger differentiation between the function of the microbes of those individuals consuming plant-based diet versus the function of those microbes from individuals consuming animal-based diets. So it's important not just to measure microbial composition, but also to consider measuring some sort of change in microbial function you expect your diet intervention to cause. All right, so let's dive into details about the intervention design. One of the first keys is to consult reporting guidelines during your design phase. And these different reporting guidelines are based on the study design, so cross-sectional versus, crossover designs, intervention designs versus observational designs. And the equatornetwork.org has a really nice website with all of these reporting guidelines. And if you consult these before you get started, it can jumpstart some of the questions you need to ask yourself as you're designing your study. Another important point, which hopefully was demonstrated by some of the examples I just showed you, is that a within individual design is the most robust for these diet microbiome experiments. And what that means is basically using the person as their own control rather than randomizing different individuals into two different treatment groups or into a treatment and control group. And we'll talk a little bit more about that later. You also need a fairly large sample size to identify the impact of the dietary intervention. In a 2020 paper, also by Dr. Abigail Johnson, suggested that a sample size of around 400 individuals might be necessary for those cross-sectional designs where you're not using the person as their own control, but rather you are assigning individuals into either treatment or control. And lastly, the example also hopefully solidified for you that considering measures in addition to just cataloging the microbiota membership, such as function using whole genome shotgun sequencing or specific metabolites of interest, may make it easier to detect the impact of the intervention you are conducting. So in the literature, there are pretty much two basic diet microbiome interventions that are most commonly observed. And one is this cross-sectional study design, which is at the top in A, where you might have individuals, you might give them a run-in period, and then you're going to randomize them to treatments and then evaluate the impact of that treatment. And this is without necessarily collecting any sort of baseline data on these individuals. And then the bottom panel, panel B, is showing an example of a randomized crossover design, where each person who enters into the study experiences both treatments, but they experience them in sort of a different order, decided by randomization, and there's a washout period in between. And this can be a better type of study design because now you have the within individual comparison for the diet microbiome intervention. It can be tricky to determine the length of the washout period, and we'll talk about that in a little bit. So just to reiterate, which design is preferred for diet microbiome research? This cross-sectional, where there are different individuals experiencing each of the treatments, is less preferred compared to the randomized crossover design, where each individual experiences each treatment or each individual experiences the treatment and the control. And this is the preferred method for diet microbiome research. And this was reiterated in that 2020 paper by Dr. Abigail Johnson, which talks about considerations for these diet microbiome experiments. They suggested a screening pre-enrollment into the study. They also suggested that for diet-focused research, the participants are trained how to actually keep track of their diets. And then after that point, the participants are randomized to either experience treatment A or treatment B first. They all experience a washout and then get switched to the opposite treatment or switched to the control. And you'll note here they have suggestions for collecting dietary data 5 days prior to beginning the treatment and collecting microbiome samples 3 to 5 days before beginning the treatment. And then again, repeating these dietary and microbiome analyses during the last 3 to 5 days of each treatment period. And so how long should this washout period be? Well, if you're only trying to look at compositional changes in the microbiome, there's a lot of evidence that those compositional changes can take place within 24 to 48 hours. And indeed, in a different paper by Abigail Johnson in 2019, they demonstrated that 2 to 3 days worth of dietary data is plenty in order to determine the relationship between diet and microbiome. They did mention that this might depend on an individual's stooling frequency. So if an individual is fairly constipated and not stooling very frequently, stooling on the order of more every 3 to 4 days, you might need a longer period of diet data. Okay, so we've discussed the crossover as being one of the best ways to conduct diet microbiome research. Now, if you're interested in just a single component of a diet rather than an overall dietary pattern, one question you also have to grapple with is whether or not to control for dietary intake. And if you look at the literature, the most successful, and that I'm interpreting that as being the papers that have seen an impact of their dietary intervention, actually use controlled diets for their participants. So they're not typically using free-living individuals consuming their typical diets. Usually they're providing the background diet to the individuals. And this makes it, if you use a controlled diet, it makes it much easier to detect the impact of the dietary component of interest. However, it might be disappointing for people out in the real world who see your research featured on the news and have decided that, X dietary component is going to increase their bifidobacterium. Well, when they try to add X dietary component, and then they send their sample off to be analyzed and find out it didn't increase their bifidobacterium, they might be annoyed with you because, yeah, your research said that, but they're not eating that defined diet, which was the background by which that dietary component was able to have its impact. So obviously, it's useful to understand what happens in a controlled diet situation, but what the public is interested in is what's going to happen when they consume that food. And speaking of the public and your participants, generalizability of your results are going to depend on the sample that you're able to recruit. And unfortunately, at least in the US, it's changing a little bit, but for a long time, much of the published diet microbiome literature really consisted of homogeneous populations of adult humans. Typically, they were white, middle to high income, and college educated, or even with more education. So to improve the generalizability of our results in the diet microbiome sphere, we really need to make efforts to recruit a diverse study population from not only a race and ethnicity perspective, but also from a socio-demographic perspective. And to improve the ability to detect an impact of your intervention, you might actually want to choose a homogeneous study population. So you have to consider what your end goal is as you're making these considerations for designing your study. Some other factors you might want to consider for potential stratification include the geographical area of your participants. Now that might be which country are they living in, or it might be do they live in a farm versus living in a city. You should consider their typical diet. If you're not controlling for diet, you should be collecting some dietary information. You should consider if these participants have pre-existing health conditions and try to either enroll all people with the same health conditions or enroll individuals with no health conditions. You might want to consider their water source. If the water source is a treated urban water system versus a well versus a forest in the middle of nowhere, the water source may have a large impact on their gut microbiome. And finally, some individuals have suggested that considering the gut bacterial enterotype as you are baseline randomizing participants into treatments might be useful. There are other types of clustering too. A lot of times you might hear about sort of the Prevotella versus Bacteroides dominant microbiomes. Sometimes people suggest there are 3 enterotypes, Prevotella versus Bacteroides versus Ruminococcus. And really you could cluster the people that you are trying to randomize on your own using something like Dirichlet multinomial modeling if you wanted to. But considering the background enterotype as you're assigning people to the diet intervention could be useful and improve your power to detect an impact. Moving on to actually getting those samples. So typically, if you want to measure microbiota composition, it's best to either be able to store that stool sample right away after the participant produces it, or to use a preservative in order to stabilize that composition. And there are many options out there for that. If you want to use the stool sample for more than just figuring out microbial composition, then you probably want to think about that a little more carefully and either not use a preservative or use something like 95% ethanol, which might enable stabilization of composition as well as metabolomic type analyses. The main point I want to make is that your samples should be collected and processed the same way within a study. So you don't want one person snap freezing their sample and another person holding on to their specimen for 3 days at room temperature. If all the samples are collected and processed in the same way, within your study, you will have within study validity, and so you will understand the impact of the treatment. Now, what you observed may not be what someone else observes if they use a different collection or processing method. So making comparisons across studies that have used different sample collection or processing methods is complicated. And if you know you want to compare your results to those from a specific study, then you should match your collection and processing methods as closely as you can. So when you're getting those samples, it's really important to collect some metadata, the time of day and date the sample's collected, how the sample was stored until shipment or delivery to the clinic. Temperature is really vital because microbes love to grow in like hot, warm environments. Any medications the participant might be taking. Of course, antibiotics are of interest, but any other medications might also interfere with the microbiome. Dietary supplements that individual might be taking. And as we mentioned, the recent 2 to 5 days worth of dietary intake. And if you're sampling infants, it's really important that you have recent measures of the extent of human milk exposure that infant has had in those 2 to 5 days before getting the sample. We mentioned the water source, and then also the stool consistency or form. And this can help you understand sort of the hydration or water status of the large intestine, and the has been shown to be associated with different microbial compositions in the stool. So some take-home points. The diversity of gut microbiomes makes these studies challenging. My microbiome is different from my grad student's microbiome, whose is different from our undergrad student's microbiome. And even if you put us all on a defined diet, our microbiomes are still going to be more like our own than they are to be like the other person's microbiomes. So that makes these types of studies challenging. And it's also what makes the within individual design the most robust study design for diet microbiome interactions. You're going to need a relatively large sample size, even with the within individual. We said around 500 maybe for cross-sectional. You might be able to cut this in half to around 200 or 250 for a within individual design. You should include measures in addition to measures of microbiota membership, so functional aspects of the microbiome. The generalizability of your results are going to depend on the sample that you can recruit. And going forward, I think it's really important as a field that we make efforts to recruit a diverse study population. Finally, the generalizability of the results depends on the intervention design. So controlled feeding studies, while they're most likely to detect changes in microbiomes, they also make it difficult for anyone who's not consuming that controlled diet to experience the same types of changes when they eat the food or dietary pattern of interest. And so those controlled feeding studies are less likely to be generalizable to the rest of the population. And finally, I just wanted to leave you with 2 references that I think can be really useful for anyone wanting to get a start. One is a guide to the diet microbiome study design, which I have referenced here. And the other was published in Advances in Nutrition, which is an ASN journal, and it is called The Design and Conduct of Human Nutrition Randomized Controlled Trials. And with that, I'd like to thank you for your time and turn it back over to Dr. Lesser.
Great, thank you so much, Dr. Comstock, for this excellent overview of key elements of study design. All right, so let's jump right into our second talk today from our second speaker, Dr. Levi Teagan. Dr. Teagan is an assistant professor in the Division of Gastroenterology, Hepatology, and Nutrition at the University of Minnesota Medical School. His research efforts are aimed at the optimization of patient care and outcomes through enhancement of clinical nutrition care. His current research is primarily focused on the nutritional assessment and care of individuals with inflammatory bowel disease. Dr. Teagan, thank you so much for being here today, and we now will turn it over to you.
All right. I need to reshare again.
It looks good.
Okay, perfect. I lost my window. Sorry, everybody. Technical difficulties. There's my presentation. There we go. All right. Okay, so yes, thank you, Dr. Lester, for the introduction. And yes, today we'll talk about in this talk interpretation and application of microbiome research. Here's disclosures and conflicts of interest. And so to start with, and this will actually build quite well off of Dr. Comstock's wonderful presentation, we'll largely break this talk into two sections. So the first is going to cover basic concepts important to be familiar with when interpreting microbiome research, and then we'll discuss the aspects of application. This is, and again, following Dr. Comstock, you'll see this is by no means an exhaustive list, and I do not mean to imply these are the only aspects to consider when interpreting microbiome research, but these are just some basic tenets that I feel clinicians should be familiar with, since they'll inform the application piece. So to start with, a typical 16S analysis provides a general high-level overview of the composition of the microbial community structure, but generally lacks the potential to predict the functionalities. So because of that, and as we'll see on the next slide, null 16S findings don't necessarily mean there was no effect of the intervention. Next is going to be the biogeography of the gut. We'll review that a little bit. And it's just important to appreciate that analysis of fecal microbiota does not take into account the biogeography of the gut. So this is things like the mucosa adherent microbes, just the small intestine, the small bowel, stomach, etc. And so therefore it provides only a limited window into the physiologically relevant activities of the microbiota. And then finally, and this last piece will be more specific to nutrition, just variability in nutrient flow can impact the microbiome composition and function, which is unfortunately not just as simple as measuring grams of fiber. But we'll begin with an overview of the capabilities of 16S. And it seems like most of you are going to be familiar with this based on the level of expertise from that poll at the beginning, but we'll start here. So 16S is the most common method that's going to be used to characterize the microbiome. And so that's going to be the outcome measure of focus today as we discuss interpretation and application of microbiome research. As I mentioned on the previous slide, a typical 16S analysis provides a general high-level overview of the composition of community structure, but it lacks the potential, or generally lacks the potential, to predict functionalities. The functional implications of compositional changes can be hypothesized, but oftentimes additional methods, things like shotgun metagenomics or metabolomics, are required to more directly measure any sort of functional change. This is important to appreciate when interpreting microbiome research because, again, these null 16S findings don't necessarily represent a lack of functional change. So the effects of diet on composition of gut microbiota are often difficult to measure, again, due to this strong inter-individual and temporal variability. And Dr. Comstock had a similar image, but this is just demonstrated by the image on the screen. So in this is just some prelim analysis of some data that we have, and just each color here is associated with an individual. Each point represents a longitudinal sample over the course of a crossover dietary intervention. And as you can see, individuals tend to remain within their unique space. And again, this is in large part the result of a phenomenon referred to as functional redundancy, where various taxa can perform the same function and are therefore capable of supporting a stable microbiome in response to perturbations such as a diet intervention. When we talk about microbiome studies, what we're most commonly referring to are studies based on the microbiome measured in stool. While the colon harbors the largest bacterial load and diversity, which is to appreciate it orders of magnitude above the stomach, the small intestine, an intestinal microbiome does exist along the length of the entire GI tract, starting with saliva in the mouth and all the way to the stool. So this figure is just a rough recreation of some of the findings from this Vasapoli paper. And it's just meant to simply illustrate that somewhat obviously microbiome composition changes throughout the length of the intestine, given the variability in environments, are obviously going to change. And so it's important to appreciate that what we are measuring in stool, while a great proxy, is still just a proxy and doesn't represent the entire microbiome, even though a lot of times we just reference it generally as microbiome research. Again, though, the colon harbors the largest bacterial load diversity, so stool microbiome does provide an excellent target, but there are clinical implications of microbiome at these other levels that haven't been fully elucidated. Beyond clinical implications, there are also potential implications for things like the microbiome in the small intestine when it comes to potential nutrient flow to the colon, which will come up again here shortly. But focusing our attention more locally just on the colon, even here, we can see that a gradient is observed. And so overall, the microbiome along the length of the colon aligns much more closely with fecal samples compared to, say, the stomach or small intestine. But it's important to appreciate that a biogeography exists even in the colon that isn't necessarily captured via stool samples. This biogeography, importantly, can impact microbial metabolites with the potential to affect various aspects of host physiology, which ultimately is what we care about, but it's not necessarily captured in stool. So there's an implication here, I'll try to get out in front of this, that stool samples, and there's some consideration around this, that stool samples might not be the best measure of microbiome, but they're definitely the easiest to study, which in and of itself has a lot of inherent value. So in that vein, though, with regard to the gut microbiome, what may be of particular relevance to health is mucosal microbiome. And so stool is used as a surrogate for the contents of the lumen of the intestine, which represents a microbial niche, which is distinct oftentimes from the mucosa-associated microbiota. The mucosa-associated microbiota and intestinal barrier are associated with conditions ranging from inflammatory bowel disease to food allergies, but are more difficult to measure compared to stool samples, which is why we often rely on stool-based studies. But it is, again, important to be aware of what fecal samples are capturing and what we are specifically referring to when we, in most cases, are talking generally about microbiome research, which is that fecal samples are providing us with a surrogate measure for the microbiome present in the lumen of the colon and are by no means a complete picture of the intestinal microbiota. But again, there's a lot of inherent value in and a lot to be learned from collection and analysis of fecal samples as a reflection of the lumen of the colon. And so this leads us to important complexities to consider when attempting to understand nutrient flow to the colonic microbes. So it's difficult to determine nutrient flow to the gut microbes, especially in diets relying on whole foods versus like an isolated fiber supplement. Oftentimes with isolated fiber sources, the effect is fairly straightforward and can be a bit more pronounced because it supports a specific metabolic niche. But even here, there exists inter-individual variability that impacts whether or not the fiber even makes it to the colon. So one concern when you do have an isolated fiber supplement is that it's just more rapidly fermentable. And sometimes it can be fermented as quickly as by the end of the small intestine. Things become further muddied when assessing the effect of whole foods versus diet intervention. And this is in large part due to the fact that fiber in foods exists in a complex matrix, which results in multiple fiber types present in the same food, different fermentation kinetics that are much less straightforward, and therefore it can be difficult whether studying either fiber supplements or diet intervention to know exactly what nutrients are made available to the microbiota in the colon. Further complicating this story is the effect of additional diet variables such as protein and fats on a nutrient flow to the microbes. So we won't spend a lot of time on this slide, but I just wanted to include it because it will come up again here shortly when considering application. So briefly, generally, the amount of protein reaching the colon tends to be positively correlated with the amount consumed. Fat itself has the capacity to alter bowel movement patterns. It requires enzymes and bile acids for digestion, which can result in some endogenous protein as well as bile acid flow into the colon. And the bile acid flow itself can have independent effects on the structure of the microbial community. So it's important to consider, and we'll see this with the application, kind of the broad changes that are occurring in the diet. And so when we consider application of microbiome research, well, hopefully you've started to appreciate that application of microbiome research is going to require some nuance. And so it's here at this point with kind of where we're at with current research, which is why it's important for clinicians to take more of kind of a 10,000-foot view when applying research or when reading research and seeking to apply findings. Because there are so many important caveats, again, only a handful of which were covered today, it's important to exercise caution with this progression to application. But when we look to apply the findings, it's just going to be important to identify and appreciate what exactly changed with an intervention. And so here, Dr. Comstock had this in paper in her presentation too, as she noted. It's a very highly cited paper. But I just wanted to use this, in this case, as a relatively straightforward example. So here we have dramatically different plant-based and animal-based diets. But you'll note that the animal-based diet was also very low in things like, it was practically even carbohydrate-free. So these are very extreme diet changes. And when the intervention is this extreme, it's obviously fairly easy or easier to pick up on the things that changed. But this becomes more difficult when we start to get into studying potentially therapeutic diets. It can become much more challenging to identify those differences. To highlight this more the therapeutic diets, we'll quickly review two recent diet interventions that were carried out in ulcerative colitis. So the first focused on fat and fiber intake, and then the second focused on the sulfur content of the diet. But what you'll see, even though they technically set out to do different things, is that on a high kind of a general level, they were overall kind of more similar than not. So this is our first paper here, and this again is the low fat, high fiber diet intervention. As you can see, fat was successfully reduced from 72 grams per day at baseline down to 21 grams per day on the low fat diet, and fiber was successfully increased from 12 to 26 grams per day. So the investigators accomplished what they set out to do. But you'll note some additional differences as well. Just secondarily, this occurred in the context of an increased protein intake. But overall, the investigators accomplished what they set out to do: low fat, high fiber. And this one is fairly straightforward enough. This is the second study, and again, this one sought to modify sulfide intake. So given the nature of sulfide sources in the diet, you can see that protein intake ends up being reduced. And you can also see that through this intervention, fat intake was also reduced and fiber intake increased, which ultimately is similar in that regard to the previous diet study. Ultimately, though, again, while the diets aren't exactly the same, when we're considering it in the context of nutrient flow to the colon, you can see how they likely would have had a similar effect, which needs to be considered when we're getting to the point of application. So more work will obviously shed light on the exact role of things like saturated fat or sulfide in the pathogenesis of something like ulcerative colitis. But an early takeaway from these works for a clinician, if we're considering it through the lens of application, is that both of these were shown to be successful interventions for the management of UC. And from a diet standpoint, overall, we see kind of this general shift towards a lower fat, higher fiber diet. And so this brings us to just kind of the conclusion, some of the kind of the main take-home points. So again, with regards to interpretation, the 16S, again, is going to be the most common thing that you're going to come across in microbiome literature. And it's just important to appreciate that this provides a high-level overview of the gut microbiota. And here you see I put the gut microbiota in quotes, because again, if you recall, what we're referring to as gut microbiota when we're talking about stool samples is really a measure of kind of the luminal microbiota, particularly towards the distal ends of the colon. The inter-individual variability, again, can make it difficult to identify consistent, specifically compositional changes. So this, again, still has to do with 16S. And so that's why, and Dr. Comstock mentioned that, it's important to include and important when you're interpreting to be looking for these functional measures when available, because really what you want to see is, was there an actual functional change? When it comes to application, it's important to consider not only the extent of dietary changes, but also potentially the degree of processing. And so we use the extreme examples of an isolated fiber source versus like a whole food, but in the process of transitioning to more of like a plant-based or more of a low-fat diet, did patients ultimately consume a more or less processed diet? Because again, even if similar grams of fiber, given the presence of this microbiome along the length of the GI tract, it's possible that what makes it to the colon could potentially vary. Again, though, given the number of confounding variables present in any fecal microbiome-based study at this point, we just encourage application of more kind of general themes and concepts versus very specific diet changes. That said, this is an exciting, dynamic field of study with lots of unknowns. So if you identify a finding that you want to apply to patient care, just allow for the presence of individual differences. What is successful in one patient might be unsuccessful in a different patient, and ultimately, that is okay. All right, thank you.
Excellent. Thank you so much, Dr. Teagan. Now we can shift our focus into addressing some of the many questions that our audience has had. I know that some of us may still have some questions that we want to add to the Google Docs, so please do feel free, not the Google Docs, I'm sorry, into the chat. You please feel free to type those questions in, and they will be pre-populated for us to take a look at and pose to our speakers today. So before we switch over to our speakers, I just want to take a moment to thank you both again for sharing your expertise and knowledge, and for your two very useful and informative talks today. I'm looking forward to hearing some of the questions our audience has generated for you both. So with that being said, let me move on over to our list of questions so we can begin our Q&A session. All right, so our first question I have up looks like it is directed towards Dr. Comstock, but this might be one that maybe Dr. Teagan can also join in on. Somebody from the audience had asked if you could possibly discuss how, or the process of maybe avoiding pseudo-replication.
Sure. So randomized crossover designs have been around for a long time, and there are a lot of statistical methods for dealing with repeated measures. And so just taking into account that random effect of the individual in your analyses is important. There are also some hierarchical models that can be used in data analysis. And I think there is maybe an upcoming webinar, or there was a webinar that focused on analysis considerations. And so it might be important to take a look at that information. Also, this microbiome types of analyses generate a lot of data. So if we're not just looking at diversity measures, which provide a single measure for each person, if we are looking at like all of the different taxa, then we will always be applying false discovery rate correction to any sort of p-values and analyses that we are doing in order to try to limit making observations that may not be repeatable or may not be sort of true observations. In ecological research, it's really hard to avoid pseudo-replication because ecological systems have a lot of collinearity. So it is something to consider. I think Dr. Jens Walters has quite a few papers where he discusses some of this, including a recent one in 2020 from the journal Cell. And his work is something you could look at to get a better understanding of that and considerations.
Excellent. Dr. Teagan, do you have anything to add to that?
I do not. Thank you, though.
No problem. All right, let's see. Another question about, let's think more on the study design route. Some consideration on how to best conduct a power calculation for when it comes to designing a study for microbiome research. And that could be for either of you. There wasn't a specifically directed person for this.
I'll defer to Dr. Comstock. She'll have a much better answer.
I doubt that I'll have a better answer, and I'm probably going to have a dissatisfactory answer to those of you in the audience. It's really difficult to determine a sample size for microbiome studies. It's pretty easy. You can use your expected changes in alpha diversity to use sort of traditional power calculation methods to determine a sample size. But if you want to think about, am I going to detect a change in a single ASV or OTU or microbial taxa out of the thousands of taxa that I'm measuring, trying to get a really good estimate of the sample size you really need to use is very complicated. There are some packages out there for R. There are some packages out there for other statistical programs that have been applied to microbiome research to start helping people make these power calculation decisions. If you can't do it in 100 people, you're probably going to have difficulty observing any sort of impact, most likely, unless you have a really well-controlled diet and a really well-controlled outcome. But that's not based really on any sort of fact. That's more based on anecdotally thinking about the literature. So I'm sorry that I have a very dissatisfactory answer about that piece of things.
Yeah, and I think that just, oh, sorry.
No,
I was
go
gonna say
ahead.
that just, that raises a good point just about, yeah, when you're kind of doing the power calculations, if there is a more relevant kind of functional outcome or clinical outcome that you're interested in, that can be an easier way to design based around that.
Excellent. This probably looks like maybe our last question, not wrap up, but around these specific topics in study design was something that was not discussed is the use of bioinformatics to analyze the data that you are collecting. There are literally hundreds of pipelines now. How do you know which to choose, and how do you know the bioinformaticists you work with is using the right type of pipeline? Different pipelines will give you different microbiome diversity profiles. Another question for both speakers today.
Sure. I mean, I think that's the topic of a whole nother webinar is analysis of this type of data on that side. I think you need to consider what you're really interested in, what result you're most focused on. Are you interested in changing diversity? Are you interested in that clinical outcome? And that's how you decide what sort of pipeline you want to use to analyze your data. I mean, we've done some experiments where we've run one analysis pipeline, a different analysis pipeline, and you get different answers, but they're only really usually slightly different in terms of the major take-home points from the results that you're getting. So I wouldn't say you get dramatically different answers depending on the pipeline, but you can get slightly different answers. You can feel more confident if you run 3 different pipelines and you get the same answer, then you can feel really strongly that what you've done is generalizable. And you know, you really For collaborations, you want to find someone you trust who has experience doing this type of analysis. You don't want to just work with someone random. And that, I think, is the best way to feel confident in the bioinformatics side of what you're doing.
Yeah, I would just second that. It's just, that's its own area of expertise. And so it's just a matter of if you do have a collaborator, there is a matter of trust there, but you have to trust, just like you're the expert in whatever you're coming into the collaboration with, that they're going to be an expert in the analysis side.
Excellent. A couple of other study design type questions when considering moving forward with this area of research. Dr. Comstock, you had mentioned water source as something to consider in collecting some of that metadata. How can water source impact the composition and abundance of the gut microbiome? Do you mind expanding a little bit on that?
Sure. Well, if you're working with research populations that are in a US city, you probably don't have to worry too much about it because most municipalities employ similar types of water treatment. But if you work in an area where you have a lot of rural participants who might be having wells as sources of water, the microbial load of those water sources can differ depending on how the individual is caring for their own well and where they're getting their water from. Similarly, if you work with international populations, some individuals' drinking water is coming from sources that are untreated, in which case there'll be a much higher microbial load that will need to be taken into consideration. If you're working with infants, it can be helpful if they're being fed formula that parents are reconstituting with water to find out if they're using distilled water, if they're sterilizing water before using it, or if they're just using tap water, because that can also induce sort of different background microbial measurements in your data.
Thank you. Question for Dr. Teagan. Do you have any recommendations regarding the preferred symptom surveys?
Sure. Yeah. So I think the collection of the Bristol stool scale information is informative, and then otherwise probably the easiest to employ is the IBS symptom severity scale. So IBS SSS is the acronym for that. It's just 5 simple questions, and it provides a pretty meaningful quantitative measure of somebody's IBS type of symptoms.
Thank you. Another participant consideration question. This one, it looks like it was directed towards Dr. Comstock. You made some great points about what to think about when designing a study. What are your thoughts about sleep patterns and how it may affect the microbiome? Do you think this is something worth controlling for in a study?
So as far as I know, there are a few studies out there that have looked at the impact of sleep on microbiomes. Something that can be conflated when you're considering sleep is sort of frequency of food consumption and also intestinal transit times. So people who are eating more frequently may have more intestinal transit times. If you stay up late, you might be more likely to be snacking, or if you are sleep deprived, you might be more likely to be snacking. And so I think some of the sleep relationship to microbiome might actually be conflated with some of this dietary exposure and also metabolism changes that occur when you're not taking the rest that your body needs. I do think it is a future area we really need to dive into and try to differentiate what is causing those changes when sleep curtailment or people who have short sleep might have changes in their microbiomes. But it's definitely an area that deserves more attention and certainly could be collected, but I don't know if it's necessary to control for it at this point if you're controlling for some of those other variables we discussed.
Okay, we have time for one last question that I think you touched on a little bit in your talk, Dr. Comstock, but we had a couple people ask what is an appropriate washout period for a crossover design for microbiome studies, and how long do individuals need to be exposed in an intervention? So basically the time of exposure in an intervention and the washout period before starting measurements. And that will be our last question for today.
Sure. So it depends on what your outcome is. So if you just want to see differences in microbiome composition, I think the literature has clearly demonstrated that you might be able to see those changes within 24 to 48 hours if your dietary intervention is going to impact microbial composition. But if you are interested in a longer term phenotype change or a metabolite change, then you might need to have much longer exposure to your intervention before you're capable of detecting a change in those outcomes. And that really depends specifically on the outcome of interest. So if you want to see a change in blood pressure, I don't know if you're going to see that change within a week of feeding the food. You might need a much longer time period. That said, some metabolites are created immediately, so the functional analysis of metabolites, you might also be able to get away with a very short intervention period. And then the washout period, of course, needs to take into account the length of time it takes to change whatever it is your outcome of interest is. So if it only takes a few days to change your outcome of interest, you can probably do your washout period for maybe twice the length of time you think the impact needs to be. If it's going to take a week for you or a month for you to see that outcome, you might need a much longer washout period before you start the second arm of your study. And so this gets to one of the limitations of the crossover study design is participant burden, is you really have to have people with buy-in who are willing to spend the time on your study, which might be multiple months of time depending on your specific details. I think Dr. Teagan has some experience with that also.
Yeah, I think as you mentioned, kind of the metabolite piece, we did some recent work with gas analysis, and that you're able to see fairly immediately with a fairly short, weekish sort of an intervention. But yeah, if you're looking for other changes, you're going to need longer. And I think, yeah, the washout period is kind of a general rule, is that it's general rule, but it's kind of like twice the length of the intervention, just to make sure if you expect something to take such a long time to change, then you need to make sure that you are well beyond that to make sure everything is back to kind of normal before you start the next intervention.
Excellent, thank you. And that is going to bring us to the end of our webinar today. A reminder to all that access to the Continuing Education Unit certificate will be provided by email after the close of the webinar. Thank you to everyone that participated and offered the great questions. An even bigger thank you again to our speakers, Dr. Sarah Comstock and Dr. Levi Teagan, for sharing their insights. Please visit the IFN's website under Continuing Education to find more great free science-based resources that have been approved for continuing education. Thank you all again. I hope everyone has a great afternoon.